first what we do in general in my group, so human robotics. So we use robotics to investigate, to understand human motor control. And on the other hand, we design robot to help human, like this robotic we share. Another example, so we work on movement augmentation. So you have this example of the people with 6 fingers. So we have studied how they can manipulate. They can manipulate better than most of us with 5 fingers. And we have application for surgery where you can a surgeon can manipulate more than 2 tools at the same time. Okay, so what I want to speak about today is about adaptive haptic sensing. So as you know, impedance control, so shaping the viscoelasticity at the hand or at the foot, at the ankle is something that human can do and have to do in order, for example, to walk smoothly or to interact smoothly with the environment. What is my presentation does? Ah, voila. So the question is whether it has an influence of haptic perception. When you change the viscoelasticity, when you change your muscle activation, does it change the sensing? And of course, can the brain would the brain be able to use body viscoelasticity to improve visual haptic sensing? So consider you have to go down these stairs, and normally it's very easy. You know where you have to go, you see where you have to go, and everything is easy. Now, when it is becoming dark, then you have to help yourself with haptics. For example, you have to take the barrier and be guided from that. So we design an experiment to investigate this kind of sensing. So how sensing is changing when vision is disabled. So we have these robotic interfaces for with flexion extension. We can measure muscle activity easily with that. So this is a task. You have to follow a randomly moving target that is noisy, and so the thing is that, so in the first experiment, we can change the co-contraction to change, we can modulate the co-contraction to change the attraction to the target. And okay, so we put different noise condition. We put, so visual noise condition, we can also put different haptic noise conditions. So by shifting, by making a bias in the reference trajectory for the guidance. And so these are the results we find on the co-contraction. So this is basically the impedance, so the stiffness at the joint. So when you have a visual deviation, then the co-contraction is increasing to make the task accurate. When you have haptic noise, then conversely, the impedance is decreasing to improve the tracking of the target. So what is the principle of this co-contraction adaptation? Because, I mean, one thing is that in one case, when you increase the noise, when you increase visual noise, you increase co-contraction. When you increase haptic noise, it is decreasing co-contraction. So it's a bit difficult to understand. So we first tested the traditional model. The traditional model is that basically impedance is increasing with the error and tend to decrease to minimize energy. And when we do that, we find the correct trend for the visual noise, but this is totally wrong for the haptic noise. It would give the converse to what we find experimentally. Now we propose a new way to adapt, that is to minimize the prediction error. So you consider the prediction error in a Bayesian sense. And so you have this expression, and you see in this expression, so you consider the deviation of haptics and the deviation of vision. And the key point is that you can change the haptic deviation by co-contraction. So you have the possibility, so the brain has the possibility in principle to influence the prediction error. And on the other hand, we want to minimize energy as usual. When we simulate this model, we see that we have a very good match in the two conditions, so for both visual and haptic noise. Now we want to consider this in more natural conditions. So consider that, for example, you have to guide your daughter when she's learning to write. And so the question is, do you have to keep rigid or do you have to relax to best sense where she is going? And so we did a similar experiment. So now you have two people who are connected with a rigid connection, and sometimes one has a fuzzy target, sometimes both have fuzzy targets, sometimes both have sharp targets. So we modify the relative noise condition. So this is the same task. Now it is done by the two of them who are connected independently. They don't see what the other is doing, but they have to do the same. And the question is how they would modulate the muscle activation if they do it. Okay, so what we observe, so this is the error. So you see that, so first you have solo trial and the error is decreasing, and you have a plateau of the error, so that when you have the different conditions, then it is keeping the same value. Now, with a different noise condition, of course, you have more error when you have a fuzzy target. Now, let's see what it means for the co-activation, the co-contraction. So the co-contraction is decreasing always because you have some learning. What is important is that the co-contraction level depends sharply on the noise, on the relative noise condition. So basically, when you are sharp and your partner is fuzzy, then you have high co-contraction. And when you are fuzzy, then you lower the co-contraction. So how to interpret that? So if we see this mechanical representation of the experiment, so we can imagine that we have a planned movement, and through our muscle activity, we are connected to this planned movement, and we can modulate the interaction with this planned movement. Analyzing the prediction error with the deviation, again, we have potentially the ability to modulate the prediction error by changing the co-activation of the muscle. So when we do simulation with that model, we see that again, the traditional model that is just increasing co-contraction doesn't work, while this Bayesian model, where both partners modifies the muscle activation to minimize their prediction error, is working very well. We can, of course, predict the co-contraction in all noise conditions, so depending on my own noise and the partner's noise. Okay, so what is the lesson? So first, the lesson is that human adapt the body impedance to improve visual haptic perception. That's something completely new. So again, we knew that before that you adapt impedance to interact mechanically with the environment. But what is new is that you also change muscle activation to change the perception. And we have this model that is optimization of prediction error and effort. So what you modify, so the cost function is to consider not only the error, but the prediction error, depending on the relative noise on your measurement, your own noise, and the interaction with the environment or with a partner. And what does it mean for robots? So if you are in contact with a robot, for example, if you want to dance with a humanoid robot, then you can make that this humanoid robot is changing the interaction according to how good you are in dancing, and so helping you to so guiding, so stiffening to guide you better, or relaxing if you are best at dancing than the robot. And so a soft robot can adapt stiffness to optimize haptic information. That's something that we are implementing now. And of course, it's working well. And that's a principle that could be used by interacting robots to work better with the human user. That was my presentation.
Thank you. Thank you, Etienne.